posts. So without any further ado, I'll let Professor Kajuri take over. Sir, I think you're muted.
Yeah, sorry. Thanks, Abhinav, and thank you for this invitation. I hope all of you can see my slides. I'm going to play them now. So if they stop at some point, which sometimes happens, please let me know. Okay. Okay, so today's talk is about black holes. And I think most of you know what black holes are, at least you have some idea, especially after the movie Interstellar, which is where this picture is taken from. Chandrasekhar once described black holes as the most perfect objects in the universe. And that is because the only elements in the construction of a black hole are just space and time. Black holes are built out of space and time. I'm paraphrasing Chandrasekhar a little bit here, but in this talk, I will hope to convince you about the beauty and mystery of black holes. So the plan of the talk is, first, I will talk about the early history of black holes. Black holes have quite a checkered history, and there are several lessons to be taken from the history of black holes. Then I will talk about something called Penrose diagrams for black holes, which gives us some insight into why nothing can come out of black holes. And finally, I will talk about the infamous black hole information loss paradox, which is an unsolved problem that has been plaguing physics for the last 50 years. And I will talk about some recent progress in the black hole information loss paradox. Please, at any point, feel free to stop me and ask questions. I hope this is an informal talk where we can stop and discuss at any point. Okay, so history of black holes. Black holes were first discovered, or at least the theoretical possibility that black holes can exist was first discovered in 1916. But they were disbelieved for many, many years. For 50 years, the scientific community did not take black holes seriously. And the reason was that the biggest physicist of the time, Albert Einstein himself, was hostile to the idea of black holes. He was very skeptical that something like a black hole could exist in nature. And it was due to the efforts of the breakthroughs made by three physicists that the scientific community was finally convinced that black holes must be real. And they were Chandrasekhar, Oppenheimer, and Roger Penrose. And now we will see how these three physicists changed the mind of the community of physicists about black holes. So first, to introduce black holes, we have to learn about Einstein's theory of general relativity. It was in 1915 that Einstein discovered the theory of general relativity. Now, what is this theory? This is a theory of gravity. Before that, we understood gravity by Newton's laws. But Einstein showed that gravity was not a force, like Newton had thought, but it was something else completely. It was the result of space and time themselves being curved. And what causes this curvature of space and time are mass or energy. As you may know, mass and energy are equivalent. So it is energy which is present in different places that causes the space-time around it to curve. And Einstein's equations, Einstein had gave a set of equations called Einstein's field equations that let us work out exactly how this works. So mass or energy acts as a source, which in turn curves the space-time. And this whole thing is governed by Einstein's equations. But Einstein's equations are very difficult to solve, extremely difficult. It's a set of coupled partial differential equations. And even to this day, we know very, very few exact solutions of Einstein's equations. Only by making some very limiting assumptions, some idealizations, can we solve the Einstein's equations? The first person to solve Einstein's equations was also the discoverer of black holes. This man is Carl Schwarzschild, who discovered who discovered black holes by solving Einstein's equations by assuming a perfectly spherical massive object or a perfectly spherical star. So he took the source as a perfectly spherical object and he solved Einstein's equations and he obtained what the gravitational field or the curving of space-time would look like around such a star. And he found a very interesting result. The result was this, that if you take a star or an object of certain mass and keeping the mass fixed, you keep decreasing its radius. At a certain point, when its radius decreases beyond the critical value, critical radius, which is proportional to, again, the mass of the object, a black hole is formed, meaning the gravitational force becomes so strong that nothing can escape from it, which is a black hole. And that radius is called Schwarzschild radius after Schwarzschild. Now, what did we learn from Schwarzschild's work? There are some misconceptions about black holes, which we can clear now, which is that are black holes very dense? Often they are thought of as extremely dense, but they need not be dense. You see, as I told you, the critical radius of black holes is proportional to its mass. And you can do one line of algebra, and it will tell you then that the density must be then inversely proportional to the square of the radius or the area of the black hole, which means that if the black hole is very, very large or very, very massive, then its density will be very small. If you have a black hole which is 1 billion times the solar mass, then that black hole will have less density than air. So a black hole need not be dense. No, it is not necessarily dense. Does a black hole have stronger gravity than a star? The answer is no. If I am at a certain distance away from a black hole of the same mass and a star of the same mass, they will have the exact same force of gravity, which is just given by, approximately given by Newton's law, which is m by r square. So for the same mass black hole star, they will have the same gravity and the same distance, only the black hole will be much, much smaller than the star. Black holes also have a horizon. So they will have some kind of horizon somewhere around in this picture. This picture shows the black hole shadow. So somewhere inside the black hole shadow, there will be a point. There will be a circle called the horizon. And the horizon is such that if you cross the horizon, you cannot come back. Even if light crosses the horizon, light cannot return. And inside the black hole, at the very center of the black hole, there is a singularity. What is a singularity? It is a place where Einstein's theory breaks down. How does it break down? Einstein's theory predicts that at the singularity, the curving of space-time or the force of the gravitational field becomes infinitely strong. So as we approach the singularity, gravity keeps getting stronger and stronger. Anything that goes near the singularity will be torn apart, destroyed completely. But at the singularity, it seems that the gravitational force would become infinite. So we understand that there is some issue there. The theory is incomplete because infinity is not a prediction that we can ever check. So the theory breaks down at singularity, and we're still trying to figure out what is the correct theory that applies that can solve the issue of singularity. And when black holes were originally discovered, both the horizon and the singularity appeared to have infinities in them. This was because the mathematical formalism at the time was not well developed. We still did not fully understand how to mathematically describe black holes. So even horizon, which we now know as simply the point of no return, seemed to have some kind of infinities associated with it. And this was one of the reasons which Einstein was disliked, which Einstein thought was there cannot be real systems. Infinities should not appear in real physical systems. So he was deeply skeptical of black holes. He thought they were just mathematical curiosities which can never form in the real world. So Einstein's criticism was there is no real process that can compress mass, that compress some massive object to such a small size, such as to create a black hole. And at that time, no process was known that could do that. There was no process known that could really compress mass to such a small radius that could form a black hole. So Einstein's hostility can be reformulated as a challenge to physicists. And the challenge being, can there be a process which can pack in mass to such a small radius as to create a black hole? And this challenge was answered in three parts, in three steps by the physicists I mentioned, starting with Chandrasekhar. Subramanya Chandrasekhar, who was a physicist who was born in India, and later he went and worked in USA. Even from the age of 19, he was working on the question of what happens when a star dies. Stars, as you know, are powered by nuclear fuel. They produce heat by the process of nuclear fusion. But what happens when they run out of the fuel, when they can no longer produce heat? At that time, when a star runs out of fuel, when a star dies, there are two forces at play. One is the gravity of the star, which is the gravity of the star itself, which is trying to crush the star under its own weight. And the second force is called electron degeneracy pressure. This is the force that kind of tries to push things apart. This comes from a quantum mechanical principle called Pauli exclusion principle, which basically says that electrons don't like to be pushed too close to each other. And when they're pushed too close to each other, they start repelling each other. So this is a repulsive force that says that, kind of born out of claustrophobia of electrons, which is saying that, no, we don't want to be too close, give us space. And gravity is saying, no, you kind of have to get closer and closer. It tries to kind of crush everything together. So there are these two forces, opposing forces at play when a star dies. And this graph shows what Chandrasekhar found, his computation. So this graph is about, on the y-axis, it shows pressure and gravity, and the x-axis is density. So these red lines are the force of gravity. So you can see that how the force of gravity changes for stars of different mass with their density is given by these red lines. And the blue line is the pressure. And so you can see that, for example, for lower mass stars, star of 0.6 or 0.8 solar mass, there are points where the blue and the red lines cross each other. And those are the points where the force of gravity and the force of pressure would be equal. So as the star kind of becomes smaller and smaller under the force of gravity, they would reach that point where the two forces are equal, and then it will stop shrinking further, because equilibrium would be reached between two forces. However, you see that after a certain point, there are no points where the two lines intersect. For a star that is heavier than 1.4 solar masses, there is no point of equilibrium. There is no pressure, cannot stop gravity anymore. So gravity will always win over electron degeneracy pressure, where when the star is heavier than 1.4 solar masses. This result is known as Chandrasekhar limit. This is the limit that electron degeneracy pressure can stop gravity up to. Now, Chandrasekhar did not take into account the possibility of neutron degeneracy pressure. And now we know that neutron degeneracy pressure can also stop gravity to a certain extent further. But if a star has a weight higher than 2 to 3 solar masses, there is really no stopping it from collapsing under its own gravity. So what Chandrasekhar showed us was the possibility of a natural process that could end up forming a black hole. So to answer Einstein's original challenge, Chandrasekhar showed, yes, there is a process which can potentially form a black hole, because when a star is collapsing under gravity, there is really nothing, no mechanism that can stop it. There is no mechanism that can, in principle, prevent a black hole from forming. But Chandrasekhar's result was not taken very seriously. The reason being, Arthur Eddington, the foremost astrophysicist of the time, he was very much a follower of Einstein and disbeliever in black holes. So after Chandra presented his result, Eddington, who had been studying his results, also gave a talk. And in that lecture, he said, all of this is wrong. In fact, Eddington was the first to have worked out that Chandra's result implied formation of black holes, and he was completely disbelieving it. He said, there has to be some mechanism which would prevent it. And and he, criticized Chandra's result throughout. And Chandrasekhar was dismayed by this criticism. And there was a long, debate about this. And at the time, Chandrasekhar had written to many physicists like Bohr, Rosenfeld. Rosenfeld was Niels Bohr's assistant, and asked, like, what do they think? And all the great physicists told him that, don't worry, we believe in you, we believe in your result, we think it is correct. Eddington is just, trying to make up something to prevent black holes forming, but the physics says you are correct. And Rosenfeld, in fact, had written to Chandra saying, do not let high priests, do not let authority figures scare you. And this is a lesson that all of us can take from this episode, that just because an authority figure is saying something does not mean that that is true. In fact, we see that, because of Einstein's skepticism, a lot of physicists like Eddington were thinking that black holes must be not true. And this shows one of the follies of following authority figures. Although I think that it's not because physicists, could not think for themselves that they were following authority figures. Rather, I think this is a function of being risk averse. If someone who is an expert like Einstein is saying something cannot work, a lot of people would think that, okay, why would I take a risk in doing something that even Einstein thinks will not work, is not true. And this really shows the importance of taking risks in science, that you have to, if you believe in something, you have to pursue it, and you should be able to take risks, and you should not be deterred from taking risks because some authority figure believes that your idea cannot succeed. Okay, now let us move on to the next part of this. Of course, Chandrasekhar had shown that, quite possible there is a process that could, in principle, end up with a black hole. The next big step was taken by Oppenheimer, the movie man, who actually did his best physics work on black holes. So before the war started, before Oppenheimer became involved in the Manhattan Project, he was a professor at Berkeley. He was, in fact, one of the first, if not the first, American theoretical physicist. And he was interested in black holes. And he was, in fact, the one who worked out Chandrasekhar limit for neutron stars. And then he asked, okay, what exactly happens when a star collapses? We know that a star can collapse when its fuel runs out and if it is heavy enough. But what happens when it does? So again, he had to go back to the Einstein's equations and he had to solve them. Now the source being a star that is collapsing. So considering the energy and mass of a star that is shrinking in size, what kind of gravitational field, what kind of curving of space-time would that give? And this is what Oppenheimer and his student Snyder together solved. And they wrote this paper on Oppenheimer-Snyder collapse, which is now known as Oppenheimer-Snyder collapse. This paper, which was published in 1939, where they used a simple model. So this is a very difficult problem realistically, because realistically a star is an extremely complicated object. And it has some crazy shape and it has material inside it which behaves in complicated ways, especially under pressure. And this is where Oppenheimer did one of the things that physicists always do, which is take some idealized system, which is consider a simple system, a simple idealization. Okay, I mean, all of you would know the joke where a farmer asks physicists about cows are not giving milk, and the physicists solve the problem and say that I have found a solution, but it works for spherical cows in vacuum. Now this is typically a joke on physicists that they solve the problems for spherical cow type systems, but it's actually one of the strengths of physicists that we can find such idealizations which strip off all the inessential parts of the system and focus on the essential processes, so that it gives us, we can solve those problems exactly and find the understanding, the insights that are needed to understand the system. And finding such idealizations is indeed an art. In some sense, more art than science. And Oppenheimer was very good at it. And he found a kind of idealization, making things very, very simple. He considered a perfectly spherical model with dust. So there is no, dust means here that there is no inner equation of state that one has to worry about. And he modeled the black hole. The results he got, resemble the real world black holes very, very closely. And so what he found was simply that what was expected when such a star collapses, indeed a black hole forms when it crosses the horizon. And he had worked out all the details. So at this point, of course, people should have believed that yes, Einstein's theory indeed predicts that black holes are real, because there is a process by which black holes can form. But even then, it was not taken seriously. And the reason, again, was that spherical cow kind of objection. People said, okay, so it works for perfectly spherical stars. But in the real universe, the stars are not perfectly spherical, they're not dust. So how can we say that even in the real universe, black holes can form? And at this point, things were stuck for a very long time. An intermediate step towards the solution came from Amal Kumar Raychaudhuri. And here again, there is an interesting story, which is this. Amal Kumar Raychaudhuri was a young physicist working in the Indian Association of Cultivation of Science in Kolkata. And his boss there, the director of the institute, was the famous doyen of Indian physics, Meghnad Shah. Meghnad Shah was a great physicist himself, but he was also kind of a micromanager. He was a very overbearing kind of boss. So he told Amal Kumar Raychaudhuri that you should not work on black holes. You should not work on, not black holes, general relativity. Because at that time, general relativity was not considered a promising line. It was considered to be very far away from experiments or observations, kind of an arcane topic. And Saha said, you do some chemistry. Don't do general relativity, do chemistry. And so otherwise I will fire you. So he had to do chemistry because otherwise he would get fired. But in his own time, he was still doing general relativity. And he produced a result, which is now called Rai-Choudhury's equation, which was kind of a breakthrough. It's a very simple relation, which shows that suppose you have certain objects which are moving parallelly, which start out moving parallelly. And Rai-Choudhury's equation shows that no matter what the conditions, gravity will always tend to focus those parallelly moving objects to a single point. This is a property of gravity, that it tends to focus things to a point, which is something you would expect because gravity is an attractive force. Now, this gave us a way of kind of overcoming the objections that were raised against Oppenheimer's results. Because now, even if you think about it a little bit, if everything is being focused, then even if a star is doesn't start in a perfect sphere, you would expect all of its constituents to kind of end up at the same point. And this was the kind of idea that was made very rigorous by Roger Penrose. Now, Roger Penrose was a physicist who initially started as a mathematician. So he had, idea of a lot of mathematical tools. So at the time, people who were trying to understand black holes and whether they form were doing it in a very complicated way. They were thinking about, okay, if it is not a perfect sphere, let us consider a small deviation from a perfect sphere and then solve the equations, see what happens. This is very, very complicated. You have to solve a lot of coupled partial differential equations. But Roger Penrose, and the lesson from Penrose's work is that sometimes the right mathematical tools, right novel mathematical tools, can unlock new physics. And Roger Penrose brought some new mathematical tools from his background in maths, and he used the tool of topology. And together with topology and using Rai-Choudhury's equations, he gave a very elegant mathematical proof that black holes must form. They are not just can form; they must be very, very generic. They are completely inevitable. So after Penrose's proof, which I won't go into because it's quite mathematical, but it's based on the idea that Rai-Choudhury's equation says that every particle gets focused to a point, and combining that with certain topological tools, one can show that singularities are inevitable. So it was only after Roger Penrose gave this proof that there was no further room for objection. I mean, mostly people agreed that, okay, now we believe that black holes are real. So to conclude the early history of black holes, this is roughly the timeline that in 1916, Schwarzschild discovered the theoretical possibility of black holes. In 1935, Chandra showed that there is a process by which black holes can form, by which mass can be compressed into a small region. Oppenheimer showed that exactly what happens when mass is compressed into a small region, which is a black hole does form according to Einstein's theory. And then Penrose showed that black holes are inevitable, that not just perfect spheres, any star collapse would result in a black hole. And then astronomers started looking for black holes, and eventually we had an indirect detection of black holes in 1971. And by now we know there are many, many black holes. We have a lot of indirect and direct evidence of black holes. And we believe we have taken photos of black holes. We now know very well that black holes are real. But it took 50 years for physicists to come to believe that black holes could be real and start taking their detection seriously. Okay, so this concludes the first part of the talk, which was about early history of black holes. And now I'll tell you about something called Penrose diagrams for black holes, which gives a little bit of insight into what black holes are. But if you have any questions up to this point, please go ahead and ask. Okay, so let me continue. Now I will show you something called Penrose diagrams, which were again devised by Roger Penrose, and they give some insight into black holes. Before we understand Penrose diagrams, let me show you a simple diagram of space and time. So in this diagram, you can see that there's a x and there's a t, there's a space and there's a time, and there is light. So this orange line is of light. Of course, you know the speed of light is 3 into 10 to the 19, whatever. But here we have chosen some unit where speed of light is 1. So we can, of course, always change the numerical value of something by choosing appropriate units. And here we have chosen units where speed of light turns out to be just 1, which means that light is represented in this diagram by a 45-degree line. So light goes along 45-degree lines in this. And what about anything that moves slower than light? What kind of trajectory will it have? Will it be greater than 45 or less? If you think for 5 seconds, you will realize that it has to be greater than 45 degree in this diagram because it moves slower than light. However, for anything to move at an angle less than 45 degree, it would have to be traveling faster than light, which is not possible, which is not allowed in Einstein's theory. Now, of course, when we consider gravity, space and time are curved. So this kind of simple diagram would not hold true. But Penrose found a way to represent the whole of space-time, different space-times, different solutions of Einstein's equations, different possible space and times in 2 dimensions in figures where light still goes along 45-degree lines. So this is an example of such a figure, which we don't need to go in too much what this figure means. But the only thing is that in such figures, light travels also along 45-degree lines. And these diagrams are called Penrose diagrams. And what I want to show you here is the Penrose diagram of a black hole. So this diagram that you see is the Penrose diagram of black hole. The shaded part is the kind of collapsing matter or whatever star it was there, which collapsed to form the black hole. There's a line which says the horizon, which is the point if you cross, you cannot come back. And there is a dashed line which says the singularity, which is where gravity becomes extremely, infinitely strong. Now, if you study the diagram, you will see that here rays of light, remember, move at 45 degrees. So if you start a ray of light somewhere, in the left, outside the horizon, at any point which is below the horizon, and from the left, it will go to this line, which is written as I plus. And that line represents far away. That line represents infinite future. So those light rays will go to the infinite future. And if you consider any point which is to the left of the horizon, left and upwards of the horizon, no light can reach the I plus. No light can reach the future. All light rays going along 45-degree lines will reach the singularity, which means, and this is what black holes are all about, that if you cross the horizon, if you go inside the horizon, there is no way for you to escape the singularity. You will inevitably hit the singularity. So in this diagram, again, the vertical axis is time, and the horizontal axis is some kind of radial direction. So you can think of spherical polar coordinates where only the radius direction is being shown here. And so singularity sits there, and nothing can escape the singularity, because once you are inside the horizon, you obviously, because time is the vertical direction, you'll obviously progress in time and you will hit the singularity. There is no escape. Okay. And once you're inside, there is no light ray that will take you outside because light rays move 45 degrees across. Okay. So this again finish the second part of the talk. And now in the final third act, I will talk about the mystery of black hole evaporation, the mystery of black hole information loss paradox. Before that, let me pause for 30 seconds for any questions about Penrose diagrams. Okay, so let me proceed. So Stephen black holes, which seemed till then to be just inert objects that lie in our skies, can actually radiate. They give out radiation. And this result comes from combining black hole physics with quantum theory. Some of you may know about this particle antiparticle. So Stephen Hawking gave a simple way of understanding the concept of Hawking radiation, which is kind of a cartoon way. We should not take it too seriously, but it gives a good insight into how black holes radiate. And the idea is what happens according to quantum field theory, particles and destroyed. So they are created and they annihilate among themselves. However, what happens near black holes is that one of them could fall inside the black hole and the other could escape. And this escaping particle constitutes a Hawking radiation. So as a black hole radiates, as a black hole gives out radiation, of course, it is giving out energy. And when it gives out energy, it loses its mass because mass and energy are equivalent. So when Hawking radiation comes out of a black hole, it slowly starts losing its mass and it will slowly evaporate. So again, to recap, the idea is a particle antiparticle gets created near black holes. One of them falls in, the other escapes. And these two are the Hawking partners of each other. One goes in, other goes out. And the one that goes out is what we observe as Hawking radiation. And as the black hole gives out this Hawking radiation, it slowly evaporates. This results in a paradox. And to understand the paradox, we have to talk a little bit about quantum entanglement. And again, I will give you like a cartoon picture of the black hole information loss paradox. So what does quantum theory tell us? Quantum theory says for every particle, for every object, everything that is there, we can associate a kind of quantum state. This is like a label that you can put on anything that exists. Everything from an ant to an electron to a biscuit has a quantum state. And the information about this quantum state, what exactly the quantum state is, which we can call quantum information. And one of the major principles, one of the holy principles of quantum mechanics is that this quantum information cannot be destroyed. It has to be preserved. This quantum information always has to be preserved. Okay, soon I will translate this whole thing into some kind of a cartoon picture. So bear with me if this seems complicated. And then there's a phenomenon called entanglement in quantum mechanics. This is when the quantum state is not assigned to just one object, but two objects collectively have a quantum state. So there's a single quantum state, but two objects in some way share this quantum state. And in that case, if you want to know what is the quantum state, if you want to get that quantum information, then you have to have access to both the states. And a cartoon picture for this that I'm going to use is a jigsaw puzzle. So like a jigsaw puzzle, you have to have access to both the, so this is a two-piece jigsaw puzzle, and only if you have access to both the pieces do you have the full information. Unless you have both the pieces, you don't have the full picture. So similarly, an entangled system, the full information is divided into two parts or more parts. Okay, so how does this play a role in black holes? And so again, remember that the principle of unitarity now translates to this, that if there are entangled systems, meaning if there are systems like this jigsaw puzzle, you cannot lose any of the pieces of the puzzle. If you lose them, then the information is going to be lost. Unless you access both, you don't have information. And if you lose one, you have lost information. So the rule is cannot lose any piece. Now what happens is that this Hawking radiation that comes out, and I told you that one particle goes in, the antiparticle goes out or something. So these two pairs are entangled with each other, meaning they're like a jigsaw puzzle. They're carrying information together. So when this radiation is coming out, as more and more radiation comes out, there is more and more entanglement between the black hole and the outside radiation. So there are information that is hidden inside the black hole in terms of this blue pieces, and there is information outside, which is, the full information is not there outside. So if I'm an observer I'm a scientist who is outside the black hole, and I'm trying to access the full quantum information, I will find from the radiation that they do not have the full quantum information because some of it is hidden in the black hole. This is not a paradox. The principle of unitarity that I told you does not say that the information cannot be hidden. It can be hidden. So here the black hole is simply hiding the information. The problem was information cannot be lost. So far, information is not lost, it is only hidden. But now, as the black hole radiates, it loses energy. As it loses energy, it shrinks in size. As it keeps shrinking in size, at the same time, it is producing more and more Hawking radiation. So there is more and more information that is being hidden in the black hole, that is missing from the outside. But the black hole is getting smaller and smaller. Eventually, unless nothing miraculous happens, the black hole will disappear completely, taking all the blue pieces inside it and vanishing. And at this point, there will be no information left outside, which means information would be lost. The principle of unitarity would be violated. And this is the black hole information loss paradox. Hawking's prediction of black holes radiating results in information being lost. And you might think that, okay, what prevents information from escaping somehow? And it is these three principles. If these three principles are true, then there is no escaping for the information inside a black hole. One is no faster than light transmission, which it would take for something to just escape from a black hole. That's not allowed. Another principle says small scale physics does not affect large scale physics. What does this mean? This means that suppose you want to study the physics of a stone, throwing a stone, then you don't have to worry about its atomic structure or molecular structure. So what's of course the atoms and molecules, when you throw a stone, they are at play, they are vibrating, there are some effects, but the effects are so small and negligible that you don't have to worry about atomic effects on the trajectory of a stone. So that principle holds generally, that we don't need to know the very details of microscopic physics to predict macroscopic things. Of course, we can, but it is not necessary to know. So at every level of energy or every level of distance scale, we can consider physical theories, and we can describe physics by a theory which is at that scale. And this idea is one of the things that goes here. And the other principle is that general relativity holds at the horizon. Now, the horizon is very, very large, can be very, very large, can be at a very much distance. So at those scales, we expect general relativity to hold. Near the singularity, which is very tiny, where gravity becomes very strong, we can expect that general relativity maybe breaks down. But at the horizon, where the gravity can be quite weak as it is on Earth, then there is no reason to believe that general relativity should break down. So if these things are true, then there is a paradox. Now, how would the paradox might be solved? It might be solved if information escapes. So the scenario where information escapes would look like this: is that at some point, as the black hole evaporates, these blue pieces also start coming out, meaning information starts leaking out. And before the black hole evaporates, all the information is out. All the pieces are, jigsaw puzzles are solved. There is no information hidden. Everything is outside. That is the kind of scenario that would solve the paradox. So if we look at, if we make a graph of the red pieces outside, pieces without partners outside, that we can, so of course we cannot go inside the black hole and access what is inside. So if I'm an observer, if I'm a scientist, I can count the number of pieces that are outside and without their partners. So without unsolved puzzles. So if I count the number of unsolved puzzles that are outside, I will have a graph here that simply keeps going up with time. Initially there are 3, then there are 6, and then it just keeps increasing till the black hole disappears completely when it stops. So I would get a graph which would just keep going up. Whereas in this picture, where there is no puzzle, I would get a graph which first goes up from the first picture and then slowly starts coming down in the second picture, and finally it drops to 0. That is the kind of graph I would get if I were to solve if there was a solution to the paradox, if information came out. And so finally, I will tell you about the recent developments in black hole information loss paradox. And these are based on something called the ADS-CFT correspondence. ADS-CFT correspondence is an idea or a principle that comes from string theory originally. And it's not true. So this ADS-CFT correspondence, it holds in some universe called an anti-de Sitter or ADS universe. Now, this is not our universe. Einstein's theory, allows for different kinds of universes. We live in one universe which is expanding, which is called de Sitter. And this one is called anti-de Sitter, which is kind of opposite of that. It's not an expanding universe. It's a different kind of universe. So we don't live in it. However, this universe can also have black holes. And because there is a principle of ADS-CFT in this universe, which I will tell you shortly, it is useful to study this universe. And it is useful because a lot of results that are true here also translate to the real universe. Okay, so what is this ADS-CFT correspondence? This says that suppose there is a ADS universe, and on the boundary of this ADS universe, this boundary will have, so you can imagine, for example, a can of juice. And inside the can, this whole thing is a universe, and the surface of the can is the boundary. And on this surface, there's a different theory, which is called a conformal field theory. And this different theory has the same information as the theory inside. So there are 2 different theories. One is the theory of this universe, gravitational black holes in this universe. And there's a separate theory, which is only lives on the boundary of this universe. And these 2 theories are kind of equivalent. They have the same information. So to give one analogy, you can think of a can of juice, and on the can of juice, it will be written like, what are the ingredients of the can. So if you're just reading off the boundary of the can or the surface, what the ingredients are, it will tell you what is inside. Similarly, this conformal field theory, which is outside, can tell us what is inside. And the advantage of this is sometimes we don't know what is going on inside. The theory for the black holes inside can be very difficult, complicated to solve. But the outside theory, the conformal field theory, can be easier. To give you another analogy, a lot of you often say that, I don't want to read information from a book. I will just watch a video on YouTube. That is simpler. I can process the information simply, even when the same information is present in a video and a book. And this is somewhat similar, except that in this case, you can consider that we are illiterates and we cannot actually read the book. We can only access the video. So we can think of the black holes and the ADS universe as the book, which we cannot read, and the CFT as a video, which we can actually read. So two different things, two different ways of getting information. One which we can solve, the other we cannot solve, but they have the same information. Now, in this case, what does the CFT tell us?
Hi, folks. I think the speaker might have been disconnected due to some network issues. Sorry for this. We'll try to get this sorted. Uh, Hello, Professor. I think you got disconnected a few minutes ago.
I got disconnected a few minutes ago.
Yeah.
Yeah. So how far was I? Which was the slide when I got disconnected?
Could you please display the slides?
Yeah, sure. Let me share my screen.
The
You see
one
my
after, I think.
One after this one?
You did ADS and CFT.
Okay. Here?
Yeah, I think you were almost done with this.
Okay. So, so as I was saying that here, did I give the analogy of the book and the video?
Yes, sir.
Yeah, okay. So what this gives us is a way of keeping count of the unmatched pieces outside. So ADS-CFT cannot tell us, yeah, so ADS-CFT cannot tell us, how these blue pieces or these red pieces come out or don't come out, but it gives us a way of counting the number of red pieces which are unmatched and which are outside. The number of red pieces outside which are unmatched, which are without partners, can be counted from the conformal field theory. And so then, and this was developed recently in 2019, and then there was a computation done in 2019, which followed the number of red pieces, how many are there, how they go with time. And what the result was that halfway till the evaporation, the graph goes up, the number of unmatched pieces goes up, and then it comes down. So the number comes down and goes to 0, which means that it is this scenario which actually plays out according to string theory, according to ADS-CFT. It is this scenario that works, which is the number of red pieces. Initially the number goes up, and then as the blue pieces start coming out, the number goes down. So this result shows that the black hole information loss paradox is actually solved. Somehow the quantum mechanics is saved, unitarity is not violated, all the information is coming out. But how it happens is still a mystery. So far we know that there is a region inside the black hole that forms after it has evaporated halfway through, and this region shares its information outside. And this is known as the island region inside a black hole. But how it shares exactly, whether it's through some wormholes, some kind of tunnels in space-time, these have been speculated, but this is very much an active and ongoing area of research, which we still don't know. So with that, let me conclude this talk and remind you that black holes are very much out there lining our skies inside each galaxy, and they're full of mysteries. They're full of puzzles which are still to be solved. And I hope this talk inspires some of you to take up the mysteries of the black holes. So thank you for listening.
Thank you, Professor, for that talk. It was wonderfully informative. The history of black holes and the information paradox was mind-blowing. I'm sure our audience had a lot to gain from this. I'd like to take this opportunity to thank you once again for agreeing to deliver this talk. We really appreciate it. For the audience, stay connected with the efforts of the Math and Physics Club and Krittika, the Astronomy Club, through our Instagram handles or through the WhatsApp groups you guys are already familiar with. Thank you again, Professor.
Thank you.
If you have time, we could entertain some questions.
Sure.
Hello.
Yes.
Yeah, Professor. Yeah, I had two questions.
Yeah, go ahead.
So you had said that Einstein thought that infinity shouldn't appear in real physical systems and was skeptical about the description of black holes, right? But then you also said that Penrose proved that singularities must form. So I'm a little confused. In our current theory, are infinities allowed in real physical systems or not?
No, they're not allowed. I mean, okay. So general relativity is okay. So let's put it this way. The question is whether black holes form or not, according to general relativity. So if the theory predicts a singularity is forming, we would expect it, it follows that a black hole would form. The singularity itself we believe to be unphysical, and we believe that some quantum theory of gravity will resolve this problem of singularity. So when we say that Penrose showed that singularities form, the physical takeaway from that is that black holes form, where it's not that singularities are real. So singularity, of course, we believe it cannot be real, or we believe that there is some very strong gravitational thing going on inside black holes, but it cannot be infinite. There has to be something that solves it from becoming infinitely strong. But what that exactly is, what kind of principle or what kind of quantum theory of gravity resolves it, that we don't know. However, within general relativity, as long as we stay within the theory of general relativity, Penrose's result shows that singularities will form. And the import of that is then there it must be that black holes form. So the theory predicts, general relativity predicts the formation of black holes. This is the takeaway from that. It doesn't mean that singularities are real. I hope that helps.
So does that mean that further improvements need to be made or something,
Absolutely.
so that we can refine the predictions?
What it means that the singularity, which is just at a point at the center of black holes, that is an unphysical thing because it is infinitely strong, infinite gravity. The theory breaks down, general relativity breaks down at the point of singularities. So what we need and what we expect to solve in the future, and this is a problem that maybe some of you will be interested in the future, is that how does the singularity problem can be resolved in general relativity? And the expectation now is that some kind of quantum theory of gravity will resolve that problem, because we do expect quantum theory to take over when the gravity becomes very strong. So after a certain point of strength of gravity, which or a certain scale of length, which is smaller than Planck length, what is called Planck length, we expect that the physics should be described by a quantum theory of gravity. And that is what we expect will resolve the problem of singularity. But we still don't know how that will work out. So it is still very much a kind of open problem.
All right, I think that answers my question. And I have another question as well, Professor. So the conventional uh, description or notions of quantum entanglement that at least I'm familiar with go as this, that if two objects are entangled, then knowing the state of one makes the information about the other object state certain. But then you described it in terms of information being split between objects, and about you also talked about information loss not being possible. I don't
Yes,
exactly see the connection. Could you please comment on this?
yes, that's a very good question. So what you're talking about is once you measure an entangled system, then you immediately know what the result of the measurement on the other partner would be. What I'm talking about instead is how do you describe a entangled system. So you would know that if you have an entangled system and if you have a part of that entangled system, you cannot describe it using some kind of a state vector. Whereas if it's a single system, you can describe it using a vector. Whereas if it's an entangled system, the collective system, you can assign the collective system a vector. Okay, so some psi will be describing the collective system. The individual system, there is no psi for the individual subsystem, which is entangled. And that is what I mean by saying that the quantum information or the quantum state is collectively shared by these two systems. So together they have a psi. Now, if you want to describe an entangled system, what you have to do is you have to use something called a reduced density matrix, where you kind of trace over, you take a density matrix and you trace over one of the systems. Then you have a reduced density matrix where you have erased the information about the other system, and you can describe the time evolution of this system and so on using this reduced density matrix. So the point of what I touched on this talk was that unless you have both of them, you cannot recreate the state vector. You can only access the reduced density matrix when you don't have access to one of them. And if one of them is completely lost, you will never recover the state vector that is corresponds to the joint system, which is different from what you are talking about, which is what happens after measurement. And this is what happens before measurement. This has nothing to do with measurement. Okay.
Okay. Thank you, Professor.
Arish, you could ask.
Yeah, sure. Thank you, Professor, for the wonderful talk. Sir, I've read about alternate approaches to resolve the black hole information paradox. And one problem like that, it has this it's violation of monogamy of entanglement. So I've read about firewall proposal. I just wanted to know what the islands proposal which you mentioned, what does it say about monogamy of entanglement, and how does it differ from the firewall proposal?
Right. Yeah. So monogamy of entanglement was the firewall paradox, which was simply another way of stating the black hole information loss paradox itself. So it's a kind of a, it's not a new paradox. It's another, of course, it was discovered, but it was another way of stating the black hole information loss paradox in the language of entanglement. So basically what it says was that suppose you have, suppose you have this Hawking pairs that I was talking about, and a lot of them have escaped. And then the principle is that suppose you have this Hawking pairs, they're going outside, and they have some entanglement with the outside radiation. So the question was, these Hawking pairs are entangled. So every time some Hawking pair comes out, if, okay, so put it this way, if physics has to be unitary, then these Hawking pairs that are coming out have to be entangled with newer Hawking pairs, with the older Hawking pairs which have come out earlier. And now these two are entangled, the older Hawking pairs and newer Hawking pairs, and also the newer Hawking pairs, and inside the black hole, the partner is entangled. And together, they can have only so much entanglement. The concept of monogamy of entanglement says that only two things can be maximally entangled, meaning that there is a certain thing called maximal entanglement, where this is the maximum amount of things, two things can be entangled. And if one thing is maximally entangled with another, it cannot be maximally entangled with a third thing. And so this created a issue, which was really a reformulation of what the black hole information loss paradox is. And the firewall paradox is also, solved by the island proposal in the same way, because the black hole information loss paradox is solved, because unitarity is restored. Now there is no issue of, because this is really showing that after a certain point, there is once the islands are formed, this entanglement between island, the stuff that is in the island and outside, does decrease. And so these islands can now go outside. The problem is that the paradox came from those three assumptions of locality, which is, things cannot travel faster than light and so on. Those three assumptions were also baked in the firewall paradox as they were in the black hole information loss paradox. But some of those assumptions are clearly being violated in some subtle way. And we still don't exactly understand how they are being violated. So those are things that we are still trying to understand. Something is going outside, but how? So that's still an open problem. But yeah, so I hope that helps a little bit. Feel free to follow up on that question.
No, sir. I'll have to read more.
Okay.
Professor, do you have time for one more?
Yeah, sure.
Okay, yeah. So you can go.
Sir, can you please explain CFT when it comes to black holes?
What do you mean safety when it comes to black holes?
You mentioned that CFT in CFT, we should know the ingredients from outside. After
Right.
knowing the ingredients, we can figure out what is going inside or what is there inside, right?
Right.
So how can we relate this with black hole?
Yeah, so this ADS universe that I talked about, right? So this universe can have black holes inside it. So anything that happens inside the ADS universe, the information is also in the CFT. So in any phenomena that takes place inside the ADS universe, it also kind of has some kind of shadow or some kind of you can say shadow, some kind of shadow, phenomena in the CFT also. So if there's a black hole here, there's a, everything that happens inside the black hole and so on are also reflected in the CFT in some subtle way. It is not always obvious, like what is going on and so on. So if there's a black hole, typically the CFT will have also some temperature. And all the information that is going inside, outside black hole and so on, everything is kind of imprinted on the CFT on the boundary. The challenge is to figure out which information or which question to ask about the black hole, which question to ask about the CFT that will tell us about the things that are going on inside a black hole. And we don't fully know this. We don't exactly know how to track things that fall inside black hole. We don't know exactly how to, track once the black hole is evaporating. We don't exactly know how to track how information may be coming out. But we have figured out how to track the total amount of information, the count of information, which is outside the black hole. And that is the information that, from a calculation that is purely on the CFT, that tells us that as the black hole evaporates, how that information, that the number of unmatched pairs, how it goes up and how it goes down. So that is how it works. So yeah, so in general, there's a CFT that can tell us everything about what happens inside an ADS universe, including when the ADS universe has black holes inside it. Okay.
Okay, so got it. Thank you.
If that is it, then I think we can close. Thank you, Professor, again. Thank you so much for agreeing to do this.